Hello, my name is Sami Zamzami and I'll be presenting Physics Lab 3 Black Holes. So for the intro, we made basically two experimental computational models simulating two different situations. So one was between a planet and a black hole and measuring the forces of gravitation between those, and the other was between three bodies, a spaceship, planet, and a moon, trying to start at a reasonable velocity so that they don't crash into each other. So for the equations we use Newton's second law, which is we found F net and then we did the velocity update and the position update so that we could do iterations to where the planets were going to be, and we used Newton's gravitational law as the force. So for part one, we had a couple observations, and from here we could see that we started off with basically just the mass of the star and the time intervals. And then as we ran the program, the iteration started, which basically created for us a vector for the force, and we did the perpendicular and the parallel component. And finding the average of this loop basically gave us the time and not gave us, sorry, the mass, and we calculated the average mass, which came around to about 2.3228 times 10 to the power of 34. And from that, we basically got the mass to see the system. So for part two, so we started with known constants, and we basically ran it through the equations that we talked about earlier to find the F on the moon and the F on the ship, and then we basically did some velocity and position update equations, and we ran the model. But first, we had to find the starting speed of the ship, which basically we did here, but we found it through trial and error. And I mean, I ran this, but it was very difficult kind of to see. But I mean, I kind of got it not to crash, but it was really through trial and error. So for some of the errors that could have occurred is this is only a simulation, and in real life there could be other forces that are playing around, such as forces from other planets or stars, or maybe like some type of bodies that it could crash to, or disturbances like asteroids or meteorites that weren't account for. And as well, this was trial and error to find the speed of the ship to start with, so it wasn't a sure method to find exactly the time. So what does this mean? So if we compare the net force and the change in momentum, these are kind of the same, but one of them I would say is easier to calculate or requires less variables than the other, which is change in momentum, because all you need to know is change for speed for that. And force sometimes can require the addition of multiple forces to all combine, so that could be a little more time consuming. But at the end of the day, change in momentum, um, measuring change in velocity over a really long time period or over short time periods can be very difficult and time consuming too, because you have to measure each time, and that could take a lot of time. So it probably is wiser to measure the force, as the force varies in a kind of proportional way that we can account for with integration and those type of things, and over long periods of time and long distances too. So it would be better to calculate force. So what if we added a black hole to the system, the law system we had? Well, this would make it even harder to calculate all the forces and to make a computational model that would allow for the bodies not to crash to each other. But the black hole would be the dominant figure in this arrangement, as it has the biggest mass. So either the other things would start orbiting around it, or some of them might crash into each other or crash into the black hole because of its gravitational pull. Thank you.